Hi, my name is Kepsi and welcome to my online tutorials. In this video, we'll be solving Valley View University end of semester examination on calculus of several variables. So please, this will be a very interesting engagement. Be my guest. So this particular exam is on end of semester exam 2019-2020 academic year on Sanhui session. And the course title is Calculus of Several Variables. The course code is MATE394 and the lecturer was Alfred Edu Asiome, one of my favorite lectures. Then the section A, which is worth 40 marks. Students are supposed to answer all questions there. 2 questions there for 40 marks. One is 20 marks. Then the section B, which have 4 questions. That's question 4, 5, and 6. Students are supposed to answer 3 questions there for 60 marks. That means each question is 20 marks. So before the video will end today, we'll find solution to all these questions. So watch the video till the end. So the question 1A is saying that we should show if R of t is differentiable and the magnitude of R of t is constant, then R prime of t is orthogonal to R of t for every t in the domain of R of t. And this question is worth 8 marks. So this question actually is on the dot product of vector value functions. And before we can solve this, we must know some gist. So since they say that the magnitude of R of t is constant, we'll let R of t to be equal to a constant, say C. And also you must know that when we square the magnitude of a vector, it will be equal to the dot product of the vector. So that's the gist we have to use. So what we do, we need to square both sides of this equation. And we can say the magnitude of R of t all squared should be equal to C squared. Then the magnitude of this square will become R of t dot R of t, and to be equal to C squared. So since they say that the differential of the vector value function, the vector value function itself are orthogonal. When we say 2 vector value functions are orthogonal, that means their dot product is equal to 0. So to get the derivative of the vector value function or the differential of it, we need to differentiate this equation. So since this is dot product, we differentiate this and keep this plus, we keep this and differentiate that. So we say R prime of t dot R of t plus R of t dot R prime of t. And to be equal to the differential of this is 0. That means we differentiate R of t, we get R prime of t, and keep this R of t plus, now we keep this R of t and differentiate this R of t, we get R prime of t. So what is common to them? You can see that R prime of t is common to them, we can bring it out. So R prime of t out, we'll be left with R of t here plus R of t, and to be equal to 0. So R of t plus R of t will give us 2 R of t, and to be equal to 0. Since these are multiplying, we can say R prime of t, 2 R prime of t dot R of t is equal to 0. So divide both sides by 2. Then we can say our R prime of t dot R of t is equal to 0. Since the differential of the vector value function, the vector value function itself, their dot product is equal to 0. It implies that the 2 vector value functions, that's the derivative and the vector value function itself, are orthogonal. So we can conclude that since R prime of t dot R of t is equal to 0, then R prime of t is orthogonal to R of t. I hope you get that. Now we'll solve the B aspect of the question 1. So the B aspect of the question 1 says that we should let R of t be equal to ln t in the I direction plus e exponent negative 3t in the j direction plus t squared in the k direction. We should find the domain of R of t, and the II say we should find R prime of t and R prime of t. And this question is worth, the I aspect is worth 6 marks, and the II is also 6 marks. So Please do well to check out my videos on the domain of a vector value functions on YouTube. So when we are asked to find the domain of a vector value function, it means all possible values of t that will make the vector value function defined. So we will exclude all values of t that will make the function undefined. So when we take all real numbers of t and we substitute to this function and this function, the function will be defined. The only problem is the lim t. So lim t, if the value of t is 0 or less than 0, the function will be undefined since it is a logarithmic function. Then we can say that the domain of this function is that a set where t is such that t is a member of all real numbers except when t is less or equal to 0. So this becomes the domain of the vector value function. Now we go to the II, which says that we should find r prime of t and r prime prime of t. So remember, our r of t is equal to lim t in the I direction plus e exponent negative 3t in the j direction plus t squared in the k direction. Please do well to check out my videos on the derivative of a vector value functions on YouTube. So when we are finding the derivative of a vector value function, we differentiate the vector value function term by term, or we differentiate them with respect to their directions. So we say our r prime of t will be equal to. Now what's the differential of lim t? To differentiate lim t, we say we reciprocate this t, we get 1 over t. We differentiate the t again, we get 1, use it to multiply. It will still be that. Now plus, this is a exponential function. To differentiate it, we differentiate the exponent and use it to multiply the function again. When we differentiate the negative 3t, we get negative 3 and use it to multiply negative 3t again in the j direction. Then the differential of this, you can do that using simple differentiation rule. We drop the exponent and subtract 1 from it. So we can therefore say that our r prime of t is equal to 1 over t in the I direction minus 3 e exponent negative 3t in the j direction, then plus 2t in the k direction. Then we need to find our r prime prime of t. Now how do we differentiate 1 over t? Remember, our 1 over t can be written as t exponent negative 1. So we differentiate this using simple differentiation rules. We drop the exponent and subtract 1 from it, we get negative 2. So we get negative t exponent negative 2, which can be written as negative 1 over t squared. So the differential of this becomes negative 1 over t squared in the I direction. Then now we differentiate this again. We differentiate the exponent, use it to multiply. When we differentiate negative 3t, we get negative 3. Times this negative 3, we get plus 9 e exponent negative 3t in the j direction. And the differential of 2t is just 2 in the k direction. Then this becomes the first derivative and the second derivative of our vector value function. This is worth 6 marks, including the domain, which is also worth 6 marks. This is the question 1. We jump straight to the question 2. So our question 2a, which is worth 7 marks, says that we should find a Taylor series representation for the function f of xy, which is equal to sine 2x plus cos y, centered at 0, 0. And this is worth 7 marks. So this particular question is on Taylor series expansion for a function depending on 2 variables. Please do well to check out my videos on Taylor series expansion for a function depending on 2 variables on YouTube. So when we have Taylor series expansion of a function depending on 2 variables, this is the expansion. Please, how this formula come about are all on YouTube. Check out my videos on that. So since this is Taylor series expansion for a function depending on the variable xy centered at AB. So since this our function is centered at 0, 0, then we can say that Taylor series expansion for this function centered at 0, 0 will be f of xy will be equal to f of 0, 0 plus the partial differentiation of the function with respect to x centered at 0, 0, and x minus 0 will be x. Then plus our partial differentiation of the function with respect to y centered at 0, 0, and our y minus 0 is still y. Then plus our partial differentiation of the function with respect to x twice centered at 0, 0. Our x minus 0 is 0. square will be x squared all over 2 factorial. Then plus the partial differentiation of the function with respect to y twice, centered at 0, 0. Y minus 0 is still 0. Y minus 0 is still y. Square will be y squared all over 2 factorial. Then plus the partial differentiation of the function with respect to x, then with respect to y. Remember, the partial differentiation of the function with respect to x, then with respect to y is the same as the partial differentiation of the function with respect to y, then with respect to x from Young's theory. So, centered at 0, 0. X minus 0 is x, and y minus 0 is also y. So, what's our task? Our task is to find the value of all these, then we substitute. So, since our function f of x is equal to sine 2x plus cos y, then we can say that f of 0, 0 will be equal to sine 2 times 0 plus cos 0. 2 times 0 is 0, so we have sine 0 plus cos 0. Sine 0 is 0, cos 0 is 1, and this becomes 1. And you can see the value of this is 1. So our next step is to find the partial differentiation of the function with respect to x centered at 0, 0. So remember, when we are doing partial differentiation of a function with respect to one variable, the other variable or variables will be held constant. So in this case, the y will be held constant. When we differentiate this, we'll get 2 cos 2x. Then since this is constant, the differential will be 0. So centered at 0, 0, this will be equal to 2 cos 2 times 0. 2 times 0 is 0, cos 0 is 1, so we have 2 times 1, and that becomes 2. So our next step is to find the partial differentiation of the function with respect to y centered at 0, 0. The partial differentiation of this function with respect to y. This, since there is no x, y element there, the whole of that will be 0. The differential of that will be 0. Then the differential of this will be sine y. So centered at 0, 0 will be equal to negative sine 0. And sine 0 is 0. So this will be 0. So our next step is to find the partial differentiation of the function with respect to x to y centered at 0, 0. So first we need to differentiate the function with respect to x. So to differentiate this function with respect to x, remember the y will be held constant. So we get 2 cos 2x. Now we differentiate this function with respect to x again. We'll get, remember we differentiate this, we'll get 2. We use it to multiply, we'll get 4. The differential of course is negative sine. So negative sine 2x. On polish this very well, we'll get negative 4 sine 2x. Now centered at 0, 0. So that will be negative 4 sine 2 times 0. 2 times 0 is 0. 4 sine 0. Sine 0 is 0 times 4 will still be 0. So our next step is to find the partial differentiation of the function with respect to y twice centered at 0, 0. So first we need to differentiate this function with respect to y. Remember the x will be held constant. So the whole of this is 0. How we differentiate that? How we differentiate it, we get negative sine y. Now we differentiate again with respect to y. So this will be negative cos y. Centered at 0, 0. Centered at 0, 0, we get negative cos 0. Cos 0 is 1. So we'll get negative 1. So our last step is to find the partial differentiation of the function with respect to x, then with respect to y, centered at 0, 0. So first we need to find the partial differentiation of the function with respect to y. The x, with respect to x, the y will be held constant. So we'll get 2 cos 2x. Now to differentiate the function with respect to y, remember the x will be held constant. Then since this is constant, the whole of that will be 0. So we can say the partial differentiation of the function with respect to x, then with respect to y, centered at 0, 0 will be equal to 0. So having gotten all these necessary values, we just substitute into our Taylor series expansion to get a Taylor series representation for sine 2x plus cos y. So remember that. So we can say the Taylor series representation for sine 2x plus cos y will be equal to f of 0, 0 remember is 1. So we get 1 plus f of x, that's the partial differentiation of the function with respect to x centered at 0, 0, is 2. So we get 2x. Then plus the partial differentiation of the function with respect to y centered at 0, 0 is 0. So we get 0 times y. Then the partial differentiation of the function with respect to x to y centered at 0, 0 is also 0. So we get 0 x squared over 2 factorial. Then plus the partial differentiation of the function with respect to y centered at 0, 0 is negative 1. So we get negative 1 times y squared over 2 factorial. Then plus the partial differentiation of the function with respect to x, then with respect to y centered at 0, 0 was 0. So we get 0 times x and times y. We can see the Taylor series expansion for this function. 2x plus cos y will be equal to 1 plus 2x. 0 times y is 0. 0 times x squared divided by 2 factorial is still 0. Negative 1 times y squared will be minus y squared. 2 factorial is 2. Then 0 times x times y is 0. Then we can say this becomes the Taylor series representation for the function 2x plus cos y, which is 1 plus 2x minus y squared all over 2. So this is the A aspect of the question 2. We go to aspect. So the question B and the C aspect of question 2 is worth 30 marks, which says that the B aspect says if r of t is equal to t plus 1 in bracket in the I direction plus t squared minus 4 in bracket in the j direction plus t squared in the k direction, we should find I, r of 1, then I, r of 3. Then the C aspect says we should find the vectors r of t that are in the coordinate plane. And all this question is worth 30 marks. So this particular question is on evaluating vector value function at a given point. Please do well to check out my videos on how to evaluate vector value functions at a given point on YouTube. So we are asked to find r of 1. That means we just substitute 1 in the place of t in r of t. So this will be equal to 1 plus 1 in the I direction, then plus 1 squared minus 4 in the j direction, then plus 1 squared in the k direction. So our r of 1 will be equal to 1 plus 1 is 2, so we have 2i. 1 squared is 1, minus 4 will be negative 3 in the j direction. Then 1 squared is 1, times k will just be k direction. Now we need to find r of 3 too. So substituting 3 in place of t in the r of t, we'll get 3 plus 1 in the I direction, then plus 3 squared minus 4 in the j direction, then plus 3 squared in the k direction. So our r of 3 will be equal to 3 plus 1 is 4, so 4i, then plus 3 squared is 9, 9 minus 4 is 5, so 5 in the j direction. Then 3 squared there is 9, so we have 9 in the k direction. The question 2. So this particular question, that's the C aspect of the question 2, is on finding vectors in the coordinate plane of a vector value function. Please do well to check out my videos on how to find vectors in the coordinate plane of a vector value function. So to do that, we need to draw a table. The first column of the table will have the plane coordinate of r of t. It's just a matter of combining all the variables or all the directions of the vector value function. So we have the xy, we have yz, and xz. This is not in any specific order. Now the zero component means which direction is missing here. You can see that if the I is for the x direction and the j is for the y direction, the z is missing and that is for the k direction. So the k is missing here. Then here x is missing, that means the I direction. Then this, the y is missing, that means it's the j direction. Now what value of r of t will make the k to be 0? So we check. It's just a matter of equating this k, the t squared to 0. So when t squared is 0, t is 0. So we say when t is equal to 0, the k direction will cease to exist. Now, the I is just a matter of equating the t plus 1 to 0. When we have t plus 1 is equal to 0, t will be equal to negative 1. That means when t is equal to negative 1, that the I direction will be. So when t is equal to negative 1 here, then the j, what to make the j direction means, that means we equate the t squared minus 4 to be equal to 0. T squared minus 4, if it is equal to 0, t squared will be equal to 4. And t will be equal to the square root of 4. And that will be equal to plus or minus 2. So we can say when t is equal to plus or minus 2, the j direction will cease to exist. So our last column, that's the vectors in the coordinate plane of the vector value function. It's just a matter of substituting these values into our vector value function. The resultant vector is the vector in the coordinate plane. So we substitute t equal to 0 in this vector value function. That means we find r of 0. That will be equal to 0 plus 1 in the I direction, then plus 0 squared minus 4 in the j direction, then plus 0 squared in the k direction. 0 plus 1, that will become 1 times I, that will be I. Then 0 squared is 0 minus 4, that will be negative 4 in the j direction. 0 squared is 0 times k, that will be 0. So this becomes our resultant vector in the coordinate plane when t is equal to 0. So this may emphasize that the k component of our vector value function will miss at the coordinate plane. So our next step is to find when t is equal to negative 1, to find that vector in the coordinate plane. So when t is equal to negative 1, that's t of negative 1. We'll have negative 1 plus 1 in the I direction plus negative 1 all squared minus 4 in the j direction, then plus negative 1 all squared in the k direction. So negative 1 plus 1 is 0 times I will still be 0. Negative 1 squared is 1 minus 4 will be negative 3 in the j direction. Then 1 squared, negative 1 squared is 1 times k, that will be k. Then the vector in the coordinate plane when t is equal to negative 1 will be negative 3j plus k. This may emphasize that the I component of the vector value function will cease to exist. Now the last one, when t is equal to positive 2 and when t is equal to negative 2. So when t is equal to 2, the positive 2, we'll have t of 2, r of 2, that will be 2 plus 1 in the I direction, plus 2 squared minus 4 in the j direction, then plus 2 squared in the k direction. This will be 2 plus 1, that will be 3. In the 2 squared is minus, 2 squared is 2 minus 4, that will be 0. So times j will still be 0, then 2 squared is 4, so we'll have 4 in the k direction. So our first vector there in the coordinate plane will be 3i plus 4k. I hope you get that. This may emphasize that the j component will miss. Now find negative 2. So r of negative 2. So our r of negative 2 will be equal to negative 2 plus 1 in the I direction, plus negative 2 all squared minus 4 in the j direction, plus negative 2 all squared in the k direction. So negative 2 plus 1, that will be negative 1 times I will be negative I. Negative 2 squared will be 4 minus 4 will be 0 times j will be 0. Negative 2 squared will be 4. So we have 4. Then our vector there in the coordinate plane will be negative I plus 4k. Then we can say these are all the vectors in the coordinate plane of our vector value function. This is all about the question 2. We go to our question number 3. So that was all about the section A, which is the compulsory aspect. Now we'll go to section B, where students are supposed to answer any 3 questions here. There are 4 questions, and students are supposed to answer 3 questions. The question 3A says that if u of t is equal to 3t in the I direction minus t squared in the j direction, and v of t is equal to 2t squared in the I direction plus 3j, we should find the derivative of the function r of t, which is equal to u of t cross v of t. This question is worth 13 marks. So this particular question is on the derivative of the cross product of vector value function. Please do well to check out my videos on the derivative of cross product of two vectors on YouTube. So since we say r of t is equal to u of t cross v of t, then our r prime of t will be equal to u prime of t cross v of t, then plus u of t cross v prime of t. So what do we need to do? We need to find the derivative of u of t and v of t, then we substitute. So we say our u of t is equal to 3ti minus t squared j, and v of t is equal to 2t squared I plus 3j. Now we'll find our u prime of t. Our u prime of t here will be 3i. We differentiate 3t, we get 3. Then the differential of this will be minus 2t in the j direction. And our v prime of t will be equal to, when we differentiate this, we get 4t in the I direction. The differential of 3 is 0, times j will still be 0. Now we substitute. So we can now say our r prime of t is equal to, remember we said it's u prime of t cross v of t. And what's our u prime of t? That's 3i minus 2t in the j direction, then cross v of t. And v of t is 2t squared, v of t is 2t squared. 2t squared in the I direction plus 3 in the j direction. Then plus our u of t, which is 3t in the I direction minus t squared in the j direction. Then cross v prime of t, and v prime of t is 4t in the I direction. So remember we said that the cross product of two vectors is just a determinant of a 3 by 3 matrix. And we can say that r prime of t is equal to, will be the determinant of, so the components form the first column, that's I, j, and k. Then we write their coefficients under them. So the coefficient here is 3. The coefficient of the j direction is negative 2t. Since the k direction does not exist, we will presume that the coefficient is 0. Then we have our 2t squared here, which is the I direction. The j is 3. The k does not exist, we say is 0. That's for that. Then plus this will be the determinant where the I, j, and the k form the first column. Then there are coefficients under them. Here will be 3t. Then the j will be negative t squared. The k does not exist, is 0. Then the I there will be 4t. Then the j does not exist, so the coefficient is 0. The k does not exist, so the coefficient is 0. So in finding the determinant of a 3 by 3 matrix, remember we said that it will be the I, then the determinant of what is not under the I. And what is not under the I is negative 2t 3 0 0. Then minus j. The determinant of what is not under the j. And what is not under the j here is 2t squared, then 0 0. Then plus k. The determinant of what is not under the k. And that's 2t squared, negative 2t, and 3. That's for this. Then plus this, the I direction again. The determinant of what is not under the I. That's minus t squared 0 0 0. Then minus j. The determinant of what is not under the j. That's 3t 4t 0 0. Then plus k. The determinant of what is not under the k. And what is not under the k is 3t 4t negative t squared and 0. Now how do we find the determinant of a 2 by 2 matrix? So we say this will be I times 0, negative 2 times 0 will be 0, then minus 0, that will be 0. So now negative 2 times 0 will be 0, 3 times 0 will be 0. then minus j. This times this is 0. Then this times this will also be 0, so minus 0. Then plus k. 3t times 0 will be 0. Then 4t times minus t squared will be plus, so minus 4t times minus t squared will be plus 4t cubed. Then plus our I for this times this will be 0, this times, so minus 0, minus j, this times this is 0, minus this, that will be 0 minus 0, then plus k, this times this. So the first k component is rather this, so we need to correct that. This will be 3 times 3, 9, then minus 2t squared minus 2t, that will be plus 4t cubed. We were doing it for the second one. We need to correct that. So now, this times this now is 0. Then minus this times this, that will be 4t cubed. So our r prime of t will be equal to, this will be 0. This, so times I will be 0. This will be 0 times j will be 0. Then we have k times 9 plus 4t cubed. This minus this is 0 times I will be 0. This minus this is 0 times j will be 0. Then we have plus k. 0 plus 4t cubed will just be 4t cubed. So since both are having the k component, we'll add the like terms. So we can say our r prime of t is equal to 4t cubed plus 4t cubed will give us 8t cubed, then plus 9, all that in the k direction. Then this becomes a derivative of r of t. Now the b aspect of the question 3 says we should evaluate the limit where t approaches 0 of 1 over t minus 1 over sine t, all that in the I direction, plus the t square in the j direction, plus 6k, plus 6 in the k direction, and that is worth 7 marks. So this question is on the limit of a vector value function. Please check out my videos on limit on vector value functions on YouTube. Hello. Okay, so to solve this, we need to evaluate or simplify that. So we have the limit where t approaches 0. We need to find the LCM, and the LCM here is t sine t. If t divides it, we'll have sine t. Multiply that, will be sine t minus t divides this, we'll get sine t divided this, we'll get t times that will be t. And all this is in the I direction. Then plus t squared in the j direction, and plus 6k. Now, when we substitute 0 into this, now when we substitute 0 here, 0 times sine 0, which is also 0, 0 times 0 will be 0. The denominator there will be 0, and to make the function undefined. So what we need to use is to use L'Hopital to solve this. So L'Hopital. So what does L'Hopital say? L'Hopital says we differentiate the numerator differently, differentiate the denominator differently, and substitute the value of the t. If it is the denominator is still 0 or is making the function undefined, we differentiate again like that and substitute. So that's all about the L'Hopital. So using the L'Hopital, we'll say this will be the limit where t approaches 0 of, now on differentiate sine t, we get cos t. On differentiate t, we get 1 all over. Now, how do we differentiate it? We differentiate this using product rule. So in differentiating that using product rule, we'll keep the t and differentiate sine t. We'll get t cos t, then plus. Now we'll keep sine t and differentiate t. On differentiate t, we get 1, so we'll get sine t. And all this is in the I direction, plus t squared in the j direction, and plus 6 in the k direction. So now let's substitute the 0 again to the denominator to see if it will be 0. So on substitute, we'll get 0 cos 0 plus sine 0. Now cos 0 is 1 times 0 will be 0. And sine 0 is also 0. 0 plus 0 will be 0. The denominator is still 0. Then we must differentiate again using the L'Hopital. We differentiate the top differently, differentiate the down differently again, and substitute. So now we say that the limit where t approaches 0 of, now we differentiate cos t, we get negative sine t. And the differential of 1 is 0 all over. Now this becomes product, so we need to use product rule to differentiate that. So we'll keep cos t and differentiate t, we'll get cos t, then plus, now we'll keep t and differentiate cos t, we'll get negative, so we'll have minus t sine t. Then we'll differentiate this sine t, we'll get cos t again. And all this is in the I direction. Then plus t square in the j direction, then plus 6 in the k direction. So we'll try substitute again to see if the denominator will be 0. So cos 0 minus 0 sine 0 plus cos 0. Cos 0 is 1 minus 0 times sine 0, that will be 0. Then cos 0 is 1 again. Then 1 plus 1 is 2. 1 minus 0 is 1 plus 1 is 2. The denominator is no more 0. Then we cannot substitute. That's one good aspect of the L'Hopital. Now we substitute. So we can say the limit where t approaches 0 of this function will be negative sine 0 over cos 0 minus 0 sine 0 plus cos 0, and all this is in the I direction. Then plus 0 square in the j direction. Since there is no t component there, we have 6k. Sine 0 is 0, so that will be 0 over cos 0 is 1. 0 sine 0 is 0 times 0 will be 0. Cos 0 is 1. All that in the I direction. Plus 0 square is 0 in the j direction. And plus 6k. We have 0. This will be 0 over 2 in the I direction. Plus 0 in the j direction. And plus 6 in the k direction. 0 over 2 is 0. So times I will be 0. 0 times j will be 0. Then we'll be left with what is 6k. Then we can say the limit where t approaches 0 of the function 1 over t minus 1 over sine t, all that in the I direction, plus t squared in the j direction, plus 6 in the k direction is equal to 6k. I hope you get that. I hope you get that. This moves straight to question 4. So our question 4a says that if a function which is dependent on 3 variables, x, y, and z is equal to 5 exponents x, y, shin z in the I direction plus cos inverse of x, y square cosec z in the j direction plus s square tan inverse of y, z cube in the k direction, we should find the curl of f, and that is worth 10 marks. So this particular question is on the curl of a vector field. So do well to check out my videos on curl of a vector field on YouTube. So we said that the curl of a vector field is just the cross product of the vector differential operator and the vector field. And what's our vector differential operator? The vector differential operator, this is giving us del over del x in the I direction plus del over del y in the j direction, then plus del over del z in the k direction. And so the curl of f is just the differential operator cross f. And what's the differential operator? The differential operator is this and the cross. And we say that the cross product of two vectors is just what? It's just the determinant of a 3 by 3 matrix. So we can say this is the determinant of 3 by 3 matrix where the I, j, and the k form the first column. So what we have? We write the coefficient of the I, j, and the k under them. So the I is del over del x, then the j del over del y, then the k is del over del z. Now under this, the I again, we have 5 exponent x, y, that's this, shin z. Then the j is cos inverse of x, y squared, cosec z. Let me shift this to this side small. So we have k del over del y. And under the y, that's under the k, we have x squared, tan inverse of y, then z cubed. I hope you get that. So, in finding the determinant of two matrices, that's the determinant of a matrix, that's the curl of f, it's just a matter of I, and the determinant of what is not under the I. And what is not under the I is del over del y cos inverse of x, then y squared cosec z, then del over del z. What is not under the I is under the del over del z is x squared tan inverse of y, then z cubed. Then minus j, then the determinant of what is not under the j. And what is not under the j is del over del x, 5 exponent x, shin z, del 5 exponent xy, shin z. Then del over del z, x squared, tan inverse of y, z cubed. Then plus k, the determinant of what is not under the k. And what is not under the k is del over del x, 5 exponent xy, shin z, then del over del y, cos inverse of x, y squared cosec z. So we have del over del x, 5 exponent xy, shin z, then del over del y, cos inverse of x, y squared cosec z. I hope you get that. So now we find the determinant of that, then we proceed. So this will be I bracket. This will multiply this minus this multiply that. So we have del over del y bracket x squared tan inverse of y z cubed minus del over del z, and del over del z times this, so cos inverse of x, y squared cosec z, then minus j del over del x, squared tan inverse of y, then z cubed, minus del over del z, 5 exponent x, y, shin z. Then plus our k, del over del x times that. So del over del x cos inverse of x, y squared cosec z, then minus del over the y, 5 exponent xy, then shin z. I hope you get that. So what next? We just find the partial differentiation of this function with respect to y. Find the partial differentiation of this function with respect to z. Find the partial differentiation of this function with respect to x in that order. Then we find the curl of the vector field. So now we find the partial differentiation with respect to their respective values. So now we find the partial differentiation of this with respect to y. Our concentration will just be on tanh inverse of y. The x squared and the z cube will be held constant. So we have x squared. When we differentiate tanh inverse of y, we get 1 over 1 minus y squared. Please check out my videos on how to differentiate inverse hyperbolic functions on YouTube. Then have z cube minus. Now here we'll find the partial differentiation of this function with respect to z. That means the x and the y will be held constant. So we have cos inverse of x, then our y squared will be held constant. When we differentiate cosec z, we get negative cosh z cosec z. Very, very important. So that's for the first one. Now we'll go to the j direction. So minus j. Now we'll find the partial differentiation of this function with respect to x. So this will be held constant. When we differentiate this, we'll get 2x. We have tanh inverse of y, z cube, then minus. Now we'll find the partial differentiation of the function with respect to z. So that means we are going to differentiate shin z. When we differentiate shin z, we'll get cosec z. So we have 5 exponent xy cosh z. I hope you get that. Then plus our k. Let me put it down here so that we understand better. Plus k. Now we'll find the partial differentiation of this function with respect to x. That means we'll differentiate cos inverse of x. The y and the cosec z will be held constant. When we differentiate cos inverse of x, we get negative 1 all over the square root of 1 minus x squared. Then y squared cosec z. Then minus. Now we find the partial differentiation of this function with respect to y. So the 5 exponent x will be held constant. When we differentiate y, we'll get 1. Then we have our shin z. I hope you get that. And all this is in the k direction. So when we polish this further, we can say that the curl of f will be equal to, now we have x squared z cube all over 1 minus y squared, then minus cos inverse of x, then y. Okay, so this negative times this negative will be positive. So we have plus cos inverse of x y squared cos z cosec z. I hope you get that. And all this is in the I direction. Now we'll talk about the j direction. So minus j. Now we have 2x tanh inverse of y z cube, then minus 5 exponent x y cosh z. Then our k direction, so plus. So this multiply this will get minus y squared cosec z all over the square root of 1 minus x squared, then minus 5 exponent s shin z. I I hope you get that. We can still polish this further. Then we say that the curl of f will be equal to x squared z cubed over 1 minus y squared, then plus cos inverse of x y squared cosh z cosec z, all that in the I direction. Then I want to say plus, so that I'll distribute this over it. So when this multiply this, it will be positive, then this will be negative. So we'll bring that one first. So plus 5 exponent s y cosh z, then minus 2x dash inverse of y z cubed, then plus all this in the j direction, then plus negative y squared cosec z over the square root of 1 minus s squared, then minus 5 exponent s shin z, and all this in the k direction. Then this becomes the curl of the vector field. So the B aspect of the question 4, which is also worth 10 marks, says that if a function f, which is dependent on x, y, and z, is equal to cosh the square root of x dash inverse of 2y link cot z, we should find the product between the differential operator and the vector field f. So to find the product between the differential operator and the scalar field, we need to find the differential operator, which is equal to del over del x I plus del over del z j plus del over del y j, then plus del over del z k. So the product between the differential operator and the vector field will be equal to the differential operator, which is del over del x I plus del over del y j, then plus del over del z k. People refer to the product between the differential operator and the vector field as the gradient of the vector field. So times the vector field, which is cosh the square root of x dash inverse of 2y, then link cot z. So what we do? This will multiply each of them. So we say that the product between the differential operator and the vector field, or the gradient, will be equal to del over del x, then times cosh inverse of root x, then cosh of root x tan inverse of 2y link cot z, then that's in the I direction, then plus del over del z, so this times this plus this times this, then plus this times that. That's all what we are doing. Then plus cosh root s dash inverse of 2y link cot z, and that in the j direction. Then plus del over del z cosh root x, then dash inverse of 2y link cot z, and that is in the k direction. So what do? We find the partial differentiation of this function with respect to x. Find the partial differentiation of this function with respect to y. Then we'll find the partial differentiation of this function with respect to z. So you can say the product or the gradient of the differential of the vector field or the scalar field actually will be equal to. Now, how do we differentiate the function? The differential of this will be sin the square root of x all over 2 root x. Please do well to check out my video on how to differentiate hyperbolic functions on YouTube. Then we have dash inverse of 2y, then ln cot z, and that is in the I direction. Then plus, here we find the partial differentiation of this function with respect to y. That means the cos root x and the ln cot z will be held constant. Our attention will be on this one. So we have cos root x. Now we differentiate this function. We'll get 2 all over 1 minus 4y squared. Then ln cot z. And that is in the j direction. Then plus del over del z. Now we'll find the partial differentiation of this function with respect to z. Cos, so with respect to z, the x and the y will be held constant. So we have cos root x dash inverse of 2y. Then when we differentiate this function, remember we will have to reciprocate. When we reciprocate this, we'll get 1 over cot z. Then we differentiate cot z. When we differentiate cot z, we get negative cosec square z. And that is in the k direction. So, polish this further, we can say that the product between the differential operator and the vector field or the scalar field, which is also known as the gradient of the scalar field, will be, we have here sin root x dash inverse of 2y all over 2 root x, and that then we have ln cot z at the top also. So we have sin root x dash inverse of 2y ln cot z all over 2 root x, and that all is in the I direction. Then plus, this will be 2 cos root x ln cot z all over 1 minus 4y squared, and that is in the j direction. Then plus, this will be, because of the negative here, we have negative cos root x dash inverse of 2y cosec square z all over cot z, and all this is in the k direction. Then this becomes the product of the differential operator and the vector field or the gradient of the scalar field. I hope you get that. So our question 5a says that if a function f which is dependent on x, y, and z is equal to cos the square root of x, y cubed z square in the I direction plus 3x square dash inverse of 2y z that in the j direction plus y square x e exponent dash tan z, and that is in the k direction, we should find the divergence of f, and this is worth 8 marks. So on top of the divergence of a vector field is just the dot product between the vector differential operator and the vector field. And what's our vector differential operator? The vector differential operator del is equal to del over del xi plus del over del yj, then plus del over del z in the k direction. So we say that the divergence of f will be equal to the differential operator dot f. And what's our differential operator? That will be del over del xi plus del over del yj, then plus del over del zk. And these dots, the vector field. And what's the vector field? The vector field is cos the square root of x y cubed z square in the I direction, then plus 3x square dash inverse of 2y z in the j direction, then plus y square x e exponent dash z, and that is tan z, and that is in the k direction. Then how do we find the dot product of two vectors? This will multiply the I direction plus this multiply the j direction plus that multiply the k direction. That becomes the dot product. So we said this will be del over del x, and I dot I, remember, is 1. So del over del x cos inverse of x, then y cubed z square, then plus del over del y, we have 3x square tan dash inverse of 2y, then z, then plus del over del z y square x e exponent tan z. I hope you get that. So on we shall find the partial differentiation of this function with respect to x. That means our y cube and the z square will be held constant. When we differentiate cos root x, we'll get sin root x all over 2 root x y cube and z square. The y and the z will be held constant. Then plus. Now we'll find the partial differentiation of this function with respect to y. The x and the y and the z will be held constant. So when we differentiate this, we get 2 all over 1 minus 4y squared, then our z. Then plus. Now we'll find the partial differentiation of this function with respect to z. So our y and the x will be held constant. So how do we differentiate an exponential function? We differentiate the exponent and use it to multiply the function. When we differentiate tan z, we get sec square z. Then we use it to multiply the function tan e exponent tan z. So I'll polish this further. We'll have sin the square root of x, then y cubed z square. You can bring the y cubed z square first, it doesn't matter since multiplication is commutative. Then 2 the square root of x, then plus 3x squared times 2, that will be 6x squared z all over 1 minus 4y squared, then plus our y squared x sec squared z e times z. Then this becomes the divergence of our vector field. I hope you get that. This is the A aspect of the question 5. Now we'll go to the B aspect of the question 5. So the B aspect of the question 5, which is worth 12 marks, we should evaluate the double integral spanning from 0 to 2 pi, then 0 to 2 of 4 the square root of 4r squared cos squared theta plus 4r squared sin squared theta plus 1 r dr d theta. And that is worth 12 marks. So we are going for the B aspect of the question 5. So this is on a problem where our surface integration results in polar integration. However, it is well simplified for us to solve. So this is just a mere double integration problem. We just solve this simply. So this will be, we can resolve this as 4. Since the 4 is constant, I will bring it outside. Then 0 to pi, then 0 to 2, 0 to 2, then This, you see that 4r square is common, so I'll bring 4r square out. Then I'll have cos square theta plus sine square theta, then plus 1. That's the square root of that. R dr d theta. So what do we have? Remember, sine square theta plus cos square theta plus sine square theta is nothing but 1. So the whole of this is 1 times 4r square, which is 4r square. So we have 4 integral spanning from 0 to 2 pi and integral spanning from 0 to 2 of the square root of 4r squared. Since this is 1, we have plus 1. Then r dr d theta. So we know that cos square theta plus our sine square theta is equal to 1. Now, we need to integrate first with respect to r. Now, look at this. When I differentiate, but first of all, I can rewrite these integrals. For integrals spanning from 0 to 2 pi, and integrals spanning from 0 to 2 of 4r squared plus 1, all exponent half r dr d theta. Now, if I differentiate 4r squared, I'll get 8r. That means this r pop up. Then I will use integration by substitution to integrate with respect to r first. So we can say we should let our u to be equal to 4r squared plus 1. Then our du over dr will be equal to 8r. Now what do we have? We can multiply both sides. So we say du is equal to 8r dr. Now I want to let r dr, so I will divide both sides by 8. Then I can say my r dr is equal to du over 8. So in place of 4r squared plus 1, I'll substitute u. And in place of r dr, I'll substitute du over 8. However, since these are the values of r, I need the corresponding value of u. So when u is 0, when r is 0, u will be equal to 4 times 0 squared plus 1. Then u there will be equal to 0 squared is 0 times 4 will be 0 plus 1 will be 1. Then the second u, when r is equal to 2, u will be 4. So u will be equal to 4 times 2 squared plus 1. 2 squared is 4. 4 times 4 is 16 plus 1. U will be equal to 17. So when r is 0, u will be 1. When r is 2, u will be 17. Then we can say this will be 4 integral spanning from 0 to 2 pi. The integral spanning from 1 now to 17. And in place of this, we write u exponent half. Then in place of r dr, we substitute du over 8, then d theta. Now this is 1 over 8. I can bring it out again. So I'll get 4 times 1 over 8 integral spanning from 0 to 2 pi and integral spanning from 1 to 17 of u exponent half du d theta. So our 4 times 1 8, that will be 1 over 2 integral spanning from 0 to 2 pi. Now we integrate this with respect to u. So remember, simple integration rule says that we just add 1 to the exponent and divide the result by, and divide the function by that result. So when we add 1 to half, remember we have 1 plus 2, that will be 3 over 2. So we have u exponent 3 over 2 all over 3 over 2, then integral spanning, that substitute 1 to 17, then d theta. So since this is dividing, you can reciprocate for it to multiply. So we have half integral spanning from 0 to 2 pi. Then we have 2 out of 3 u exponent 3 over 2, substituting from 1 to 17 d theta. What happens? This is constant. We can bring it out. So we have half times 2/3 integral spanning from 0 to 2 pi of substituting u of 3 u exponent 3 to substituting from 1 to 17 d theta. So now if half multiplied 2/3, this will divide us. So we have 1/3 integral spanning from 0 to 2 pi. Then we substitute. So we substitute 17 exponent 3/2 minus 1 exponent 3/2. Then d theta. Since this is constant, we can bring all of them out. Remember, any number, 1 exponent, any number is still 1. So we have 17 exponent 3/2 minus 1 all over 3. That's bringing that out. Integral spanning from 0 to 2 pi d theta. So when we integrate d theta, it will be theta. So we have 17 exponent 3/2 minus 1 all over 3 d theta, substituting from 0 to 2 pi. So now we substitute 0 to 2 pi. So we have 17 exponent 3/2 minus 1 all over 3. Then on substitute we get 2 pi minus 0. And 2 pi minus 0 is 2 pi. So we have 2 pi over 3. I'll let it multiply that. 17 exponent 3/2. Then minus 1. Remember, pi is just 3.142. So we get 2 times 3.142 over 3. Then 17 exponent 3/2 minus 1. So when we do 2 times 3.142 divided by 3, we get 2.0947. And 70 exponent 3/2 will give us 70.0928, then minus 1. So 70.0928 minus 1 will be 69.0928 times 2.0947 will get 144.7287. Correct one decimal place will be 144.7. Then this becomes the answer to this problem. I hope you get that. So now we'll solve our last questions on this semester examination, which is the question 6. So our question 6a says that we should state the Euler's theory on homogeneous functions, and this is worth 5 marks. So the number 6 is on Euler's theories of homogeneous functions. Please do well to check out my videos on Euler's theories of homogeneous functions on YouTube. And the question says we should state the Euler's theories of homogeneous functions. So Euler's theories of homogeneous functions states that a function f, which is depending on several variables, and for this matter x, y, and z, is said to be homogeneous of n degree if for all values of the parameter lambda, f of lambda x, lambda y, lambda z is equal to lambda exponent n, f of x, y, and z. So this is to a layman, it means that you introduce a parameter lambda to affect all the independent variables of f. If you factor out a common parameter of lambda and you get a function back, that means the function is homogeneous. If not, the function is not homogeneous. So the B aspect is giving us some functions and says that we should determine whether those functions are homogeneous. So the B aspect says we should show whether or not the following functions are homogeneous. And if it is homogeneous, we should state the degree. So the first one, f of x, y, z is equal to x exponent 4y squared sine inverse of x over y. And the II is f of x, y, and z is equal to x squared plus xy. And III is f, which is dependent on x, y, and z is equal to 1 all over x squared plus y squared. Each of these questions is worth 5 marks. So Euler is saying that to indicate that, or to find out if a function is homogeneous, you introduce a parameter lambda to affect all the independent values of the f. So that means any place we see x now, we substitute lambda x. Any place we see y, we substitute lambda y. And any place we see z, we substitute lambda z. Then we can say this is lambda x exponent 4, lambda y exponent square, or lambda y square, then sine inverse of lambda x over lambda y. We try to factor out. So this will be lambda exponent 4, x exponent 4, lambda square y square. Then we have sine inverse of lambda x over lambda y. What happened? We try to factor out a common parameter of lambda. What common parameter here? We have lambda square out. We will be left with lambda square x exponent 4, then y square, then sine inverse of lambda x over lambda y. Now the question is, did we get a function back after we factor out the common parameter? The answer is no. If no, then we say that therefore the function is not homogeneous, or in other words is non-homogeneous, or is not homogeneous. That's for the first one. Now we look at the second function. So our second function is this x squared plus xy. So Euler is saying we should introduce a parameter to affect all the independent variables. So here there is no z, so there is no need to substitute in the lambda z. So we have lambda x all square plus lambda x, then lambda y. Any place we see x, we substitute lambda x, and any place we see y, we substitute lambda y. So this will be equal to lambda square x square plus lambda times lambda will be lambda square xy. What is common here? Lambda is common. Lambda square is common. We substitute it out. We have x squared plus xy. After we substitute it out, do we have the function back? That's x squared plus xy. Yes, we have it back. Then we can say the function is homogeneous. And what is the degree of lambda? The degree of lambda is 2. Then we can say that the function is homogeneous of degree 2. I hope you get that. We'll look at the third function. So our third function is f of xy is equal to 1 all over x squared plus y squared. So we use the Euler's theory of homogeneous function. Says that we should introduce a common parameter lambda to affect all the independent variables. Here too, there is no z, so we will not substitute the lambda z. So this will be 1 all over lambda x all square plus lambda y all square. So we have 1 all over lambda square x square plus lambda square y square. What is common here? We have lambda square out, we have x squared plus y squared. We can rewrite this as lambda exponent negative 2 using indices 1 all over x squared plus y squared. Now the question is, did we get a function back? Did we get 1 over x squared y squared back? Yes. Then we can say the function is homogeneous. Now what is the degree of the lambda? The degree of the lambda is negative 2. So we can say the function is homogeneous of degree negative 2. I hope you get that. So this is all about the questions. Please play over the video and you'll become used to all these problems. So remember to subscribe to my YouTube channel before you sign out. Like, comment, because your comments keep me going. Until we meet again, my name is Kepsi.